Assalamualaikum and good evening to Dr. Ilyani. Today we will present a comprehensive overview of Flowrate measurement, Venturi meter and Sluice kit. Throughout this presentation, we will delve into the key aspect of Flowrate measurement and explore its various components including the introduction, calculation, additional notes and finally the conclusion. Our team is made up of 5 members, which is Ahmad Ibrahim, Nur Amira, Isli Fazlin, Aidan Fadlin, and Nur Dalila. Let us moving on to the introduction. In this presentation, we will know that flow rate measurement is the process of quantifying the rate at which a fluid moves through a specific point in the system. Also, it helps in controlling and optimizing processes, ensuring efficient operation and maintaining quality standard. Many types of devices using principles involved in the Bernoulli equation have been developed to measure fluid velocities and flow rates. An effective way to measure flow rate through the pipe is to place some type of restriction within the pipe, referred to figure 3.11, and to measure the pressure difference between the low velocity high pressure upstream section and the high velocity low pressure downstream section. Other flow meters based on the Bernoulli equation are used to measure flow rates in open channels such as flumes and irrigation ditch. In the first case, we assume the flow is horizontal, steady, inviscid, and incompressible between point 1 and point 2. The Bernoulli equation becomes as shown below, and we modify the continuity equation can be written as below, where A2 is smaller than A1 at the flow area section. By combining this equation, it will give the result as below. Next is the flow rate measurement in Sluice kit. With the fact that P1 and P2 equals to 0, this equation can be combined to give the flow rate as given. As we refer to the figure 3.12, the downstream depth not the gate opening A was used to obtain the result of equation 3.18, since a vena contracta result with a contraction coefficient less than 1, where typically the contraction coefficient is approximately 0.61 over the depth ratio range of 0 to 0.2. For larger value of the value of contraction coefficient, it increases rapidly. Next is the calculation. By looking at the example 3.11 Venturi meter, the question asks us to determine the range in pressure difference by giving the kerosene is 0.85 flow through the Venturi meter shown in figure E 3.11 with flow rates between 0.05 and 0.050 meter cube per second. To find the answer, we assume that the flow is steady, inviscid, and incompressible. The relationship between flow rate and pressure is given by equation 3.17. This can be arranged to give the pressure difference as given, and the final answer is we're gonna get 550 kg per meter cube.
From the previous slide, we already find the density. Then we can find the range in pressure difference. First, for the smallest flow rate, which is 0.005 meters square per second, the pressure difference is 1.16 kilopascal. Likewise, for the largest flow rate, which is 0.05 meters square per second, we get the pressure difference is 116 kilopascal. This is the answer of the range in pressure difference. This value represents the pressure difference for inviscid, steady, and incompressible condition. The ideal results represented here are independent of the particular flow meter geometry, such as orifice, nozzle, or Venturi meter, as shown in figure 3.11. Next, for example 3.12, figure show the water flow under the slide gate. Question asks to determine the approximate flow rate per unit width of the channel. First, we assume that the flow rate is steady, inviscid, and incompressible flow. So, we can apply equation 3.18 to obtain Q over B, which is the flow rate per unit width. In this instance, Z1 is equal to 5.0 meter and A is equal to 0.8 meter. So, the ratio A over Z1 is equal to 0.16, which is less than 0.2. Then we assume that the contraction coefficient is approximately Cc is equal to 0.61. Thus, we also can find Z2 by multiply Cc with A. Then we get 0.488 meter. We can obtain the flow rate by substitute the previous information into the equation 3.18. Then we get Q over B is equal to 4.61 meters square per second. Otherwise, if we consider Z1 greater than Z2 and neglect the kinetic energy of the upstream fluid, we would have the equation of flow rate per unit width is Z2 times square root of 2gz1. Then we get Q over B is equal to 4.83 meters square per second. Now let's see for the additional note. In addition, different flow measure devices may have varying operating principle, accuracy level, and limitation. Some common flow measurement technologies include orifice plate, Venturi meter, magnetic, ultrasonic, and turbine flow meters. Each technology has its own advantages, limitations, and applications. It is important to choose the appropriate flow measurement device based on factors such as the nature of the fluid, flow condition which is steady state or transient, accuracy requirement, and budgetary constraint. To summarize our conclusion, having a solid understanding of the unique measurement technologies, influencing factors, calibration, and maintenance procedures will help to ensure accurate flow rate measurement and reliable data for various applications. Accurate flow rate measurements are essential for various applications and industries, and being aware for these key aspects enable reliable and trustworthy data acquisition. That's all from our group. Thank you for watching.